elementary particle physics, which is fundamental because it attempts to discover and understand the basic constituents of matter, what the universe is made of, the stuff that makes up the universe, and the forces that act on this stuff and makes it interact, creates new structures. And this field, there's been enormous progress in the last 100 years. The field I date roughly back to 1911. In a sense, that's the beginning, at least of experimental particle physics. So it's only been 105 years, but much has been achieved. And I'm first going to describe a bit of those achievements and where we stand today, and then go on to move out towards the frontiers of particle physics and fundamental physics. Rutherford wanted to study the structure of the atom. By that time, everyone believed there were atoms. You couldn't see them directly, but they were surely there. And nobody had any idea what existed inside the atom. A few years before, J.J. Thomson had extracted, using electricity, electrons from the atom. So clearly the atom contained electrons, the first elementary particle ever discovered. But no one knew what the structure of the atom was. Nobody could look inside the atom. You needed microscopes with much more resolution than anybody had then or today, for that matter. So Rutherford invented a new technique. He used a beam of alpha particles. Alpha particles are the nuclei, it turns out, of helium atoms. And they're emitted in radioactive decay of radioactive elements. That was what Rutherford won the Nobel Prize in Chemistry for. He used a beam of alpha particles, collimated beam, and he shined the beam on a gold foil to study what happens when those particles pass through or encounter the gold atoms, and measured the deflection of these alpha particles. His undergraduate student Marsden and his postdoc Geiger actually did the measurement. They sat in a dark room for hours until their eyes got sensitized, and then they measured how the place on the fluorescent detecting screen where the deflecting alpha particles hit. And from that, Rutherford hoped to deduce what was going on inside the atom. He was very surprised at some of the results because many of the alpha particles would bounce back at a large angle. And one of the prevailing theories at the time was J.J. Thomson's model of called a plum pudding atom, where you had a homogeneous sort of distribution of the positive charge of the atom, and electrons were stuck in it like raisins. And in such a model, the alpha particles you'd expect would just go zooming through. They had so much energy. And Rutherford was very surprised when some of these alpha particles came right back at him, or at Marsden and Geiger. And so he applied the theory of electromagnetism, Maxwell's theory, to calculate what it would look like if these alpha particles were hitting an atom which actually had its charge localized in a very small central portion of the atom, which he called the nucleus. And he discovered that the data fit the thereafter Rutherford formula for scattering. If all of the charge and mass, positive charge and mass of the atom was inside a very small nucleus, which he could show was less than 1 part in 100,000 of the size of the atom. Rutherford didn't put his name on the experimental paper that discovered the nucleus because he didn't sit there and do the measurements. Geiger and Marsden were the sole authors, but his paper on the interpretation, which followed right after, was theoretical, and he deduced the existence of a very small nucleus inside the atom. That immediately had an incredible impact on physics. It suggested a planetary model of the atom. And since that classically has many problems, it led within 2 years to Bohr inventing a model of the atom, the Bohr model, which inevitably produced quantum mechanics 10 years later. But as far as our story goes, it concentrated the unknown story of matter and force into the nucleus at the center of the atom, which particle physics has been exploring ever since. But it's only been 100 years. My mother-in-law is 97 years old. 100 years, and is one human life nowadays, a very short period. Now, 100 years later, we actually still do particle physics experimentally using the same idea that Rutherford did. Well, we have fancier, bigger machines to accelerate the beams, the protons, like the LHC at CERN, and we have much fancier detectors than just the eyes of Marsden and Geiger. But the technique, the basic principle of how do you study the inside of atoms, the inside of nuclei, the inside of nucleons, and now we're trying to study the inside of quarks, is the same. You follow the method you might use to figure out what a precise, delicate watch is made out of. You take two watches and you smash them together, and then you take a picture of what happens right after they hit each other. All the parts fly out. If you take a good picture, you can identify all the components. And if you're really clever, you could figure out, well, this piece looks like, this makes this move, and you might figure out how it works. Now, with watches, we have better methods. But with atoms and nuclei and quarks, we don't. We still use Rutherford's trick, except that, as I said, we have much higher energy beams. You need higher energy to probe shorter distances. And this is the largest collider of particles. We now actually collide particles going one way with particles going the other way. That makes it even more energetic, allows us to probe shorter distances. This is the largest Hadron Collider we have in Geneva, 20-kilometer ring, 200 meters underground. This is the Geneva airport. This is a big collider. And the detectors we need to take those pictures of what happens when these beams collide and produce 10 to 20 collisions every 10 nanoseconds are enormous themselves. This is a person. This is an amazing detector. But it's what's required to take the pictures of what happens in these very high energy collisions. This is actually a picture, one of the first events recorded at the LHC 6 years ago. Now, so this 100 years has yielded amazing results from not even sure 100 years ago of the existence of atoms, much less what they were made of. We now have a rather complete theory of the structure of matter within the atom. This is not an accurate picture. You see the nucleus has been blown up to be visible. And it's made up of neutrons and protons, but now we understand that they're made up of quarks. In fact, we believe we have identified the basic constituents of matter as electron and electron-like objects, and quarks that make up the neutron and proton that make up the nucleus of atoms. Even more important, we've understood in great detail and in a deep way the forces that act on these particles, not just the force of electricity that holds the atom together, is responsible in a quantum mechanical theory of the atom for the properties of atoms, molecules, chemistry, biology, us. But also the force that holds the quarks together inside the nucleus and the force that changes one quark to another and is responsible for radioactivity. All of this is summarized in what is called, for historical reasons, the Standard Model. And what is pictured here is sort of the equations, or what replaces the equations of fundamental physics. There are a whole bunch of fields here and interactions between these fields and a variety of parameters. For most of everyday physics, 2 or 3 parameters are sufficient, but the model or the theory has 19 parameters all in all, and it's unbelievably successful, which is why I think the word model is really bad. It's not a model, it's the best theory. It's a living example of what physical theory should be. A well-defined mathematical structure with parameters that you measure, and having measured, in principle, if you were strong enough and patient enough and crazy enough, you could calculate everything, almost everything that has ever been measured. And in special cases, you put that assertion to test by calculating certain experimentally measurable quantities to extraordinary accuracy and comparing them with experiments that are done to extraordinary accuracy. So it really deserves to be called a theory. It incorporates everything we've learned just about the physical universe, especially if we include Einsteinian gravity for the last 2,000 years. Now, I want to say a bit about the structure, and I'll try to teach you something about asymptotic freedom, or what holds quarks together in the Standard Model or theory. So first of all, the Standard Model summarizes what we've learned from 100 years of search for the basic building blocks of nature. They are the quarks that make up the nuclei of atoms, and they are the electron and its partner, the neutrino, that exist throughout the atom. These are called leptons, the electron and its neutrino, a pair together with a pair of quarks. These are the particles that make up most of the matter we see in this room. But in accelerators, with energy, we can produce matter that's unstable. And it turns out that all of that matter can be summarized and understood as a consequence of there being 2 other copies or families of quarks, charm-strange, top-bottom, and together, leptons, a heavier electron, an even heavier electron, and their associated neutrinos. And as far as we can tell, and of good reasons to believe, that's it. There are certainly unlikely to be more families, at least just copies like this of the original pairs. So that mostly has been experimental discovery and careful measurement of the masses and properties of these quarks and leptons. On the theoretical side, here, in a sense, the advance is even greater because we've understood in a very deep way, in a very precise fashion, what the forces that hold these particles together and are responsible for the structures we see throughout the universe. The force of electricity and magnetism that acts on or affects all particles with electric charge. In fact, all the particles here except the neutral neutrinos. But also we've understood the strong force that holds the up and down quarks together, and the weak nuclear force, which is actually the one responsible for turning one quark into another for radioactivity. And there's one more ingredient that had to be added to explain the properties of the weak nuclear force. That's the famous Higgs mechanism, which in its simplest form produces a particle discovered 4 years ago, completing this theory. And it is unbelievably successful. If you want to make a strong claim, you could argue, and it's not really that much of a stretch, that it might very well work from the smallest imaginable distance, the so-called Planck length. I'll discuss that length later, but it's very small, 10 to the minus 33 centimeters, to the edge of the universe. We study physics throughout the universe, 13 billion light years across, and it's the same physics that works on Earth, works on stars, and allows us to explain the properties of stars. So the physics that is in a reductionist sense contained in our basic understanding works, in fact, almost too well. Now, I want to describe one feature of the Standard Model, which at first sight appears very strange, and that is that these three forces that act within the atom, electricity, magnetism, the strong and weak nuclear force, are actually at the heart of things the same kind of force. And yet they appear so differently in nature. The electromagnetic force we have all felt or know about. It is a long-range force. It falls off like inverse square law. The strong nuclear force is much stronger. You've never felt it. And it doesn't fall off like inverse square law. And yet, at the heart, they're the same, except for some strange features of the quantum world. So this is the pedagogical part, and I even will write down one or two equations, which you're never supposed to do in a public lecture. So let's consider electromagnetism. We have here an electron, and it's anti-electron. Every particle we know, believe, have observed, has an associated antiparticle with opposite charges, but otherwise same properties, same mass, same. So here's the electron, here's the positron, the anti-electron. They source an electromagnetic field. They attract each other. That's what electricity does. Opposite charges attract. And in the theory of electromagnetism, we say that the charges set up an electric field that transmits the force from one to the other. If we shake one of these charges, these field lines shake, and those ripples in the field are, as Maxwell discovered, travel with the velocity of light. In fact, that's what light is, the ripples in the electromagnetic field that transmits the force from one charge to the other. And these are the force lines. Now, you know that you can pull these charges apart. That's how J.J. Thomson discovered the electron. He pulled it by applying an electric field out of atoms. And you can do that because the force falls off, and the amount of energy it takes to pull the charges apart takes a certain amount of energy to ionize an atom, but it's finite, not infinite. So you can, if you have enough energy, you can pull the electron out of the atom. Now I'm just going to derive that. So here's the pedagogy. If I have an electron-positron distance r apart, all I need is Gauss's law. Gauss's law really captures the essence of electromagnetism and also of the strong nuclear force. So Gauss's law tells you if you draw a sphere around a charge, then the flux, the product of the electric field over the whole sphere, so this is E times r squared is roughly the area of the sphere, is equal to the amount of charge inside the sphere. So from that you deduce that the electric field at distance r falls off if you divide by r squared like q over r squared. And then you can calculate the amount of work it takes with a force E to pull the charges apart by distance dr, which will go like dr over r squared. If you try to pull them in infinite, the total energy by integrating this goes like some constant called the ionization energy minus 1 over r. So if you have enough energy, I, you can pull these charges apart. Now, the strange thing is that the strong force between now quarks, here's a quark, an up quark, it too has a charge in the theory of the strong nuclear force. In fact, it has 3 charges. So, and that's essentially the difference, the only difference between the theory of electricity and magnetism and the theory of what we call quantum chromodynamics. We use these, we label these charges by colors. Why not? Red, white, and blue charge. And in many ways, this is exactly the same as electric charge, except there are 3 of them. So the up quark here, the up red quark, will attract its anti-up red quark. In the same way, naively, as in the case of electromagnetism. Sets up a field whose source is the color charge. We call it, therefore, a chromodynamic field. And that field the force would fall off like 1 over distance squared, just like classical E&M. In the classical theory of the classical chromodynamics, we would be able, presumably, to separate these quarks. It would behave just like electricity and magnetism. The difference in the world that we observe, the real world, between the strong force and the electromagnetic force has to do with the quantum effects in the vacuum. So this is the classical picture, and it's only wrong because the world is not classical, but quantum mechanical. The quantum mechanical world differs from the classical world in many respects, but one of the most important and essential has to do with the property of the vacuum, properties of the vacuum. Now, in quantum mechanics, you all have heard of the Heisenberg uncertainty principle. And I'm going to give an illustration here of that for an oscillator, the simplest of all dynamical systems. We would say a system with 1 degree of freedom. Only one thing can happen. Oscillator moves with a given frequency like this. This is the oscillator at rest, and this is the oscillator with some extra energy moving. But if it's in its, disappeared, in its lowest energy state, it's at rest. In quantum mechanics, that's impossible, as Heisenberg taught us. If we take a quantum oscillator, where's the quantum oscillator? So in its ground state, lowest energy state, it's at rest. The quantum oscillator, Heisenberg observed that if you try to ascertain or measure that this oscillator is at rest, you must interact with it. So you look at it to see if it's at rest. What does looking mean? Well, you send a beam of light, and you bounce it off, and you see whether the oscillator is at rest or not. But according to quantum mechanics, those beams come with quantized energy, and that always creates a certain amount of motion in the quantum oscillator. The classical picture of oscillator at rest, so it's here with no velocity, doesn't hold in quantum mechanics. Even in the ground state, the lowest energy state, there's always some motion. Every degree of freedom, every dynamical system in a quantum theory is oscillating. Now, back to the strong force. These quarks are sitting here in the vacuum. They set up a field. What inverse square law? Because the underlying principle for the theory of the strong force is exactly the same as electromagnetism, except for the fact that there are 3 charges. The difference is in the properties of the quantum vacuum in which these quarks live. You might think of the vacuum as boring, empty, nothing there, nothing's happening. But in quantum mechanics, that's impossible. You look at the vacuum, you disturb it. The vacuum could be filled with all sorts of fields which you've turned off, but nothing can get turned off quantum mechanically. It's always oscillating. So this is actually a picture that of the vacuum, the way it looks, using the theory, of course, to do a kind of a simulation that gives you some picture of the fluctuating fields, the chromodynamic fields that you classically could turn off, but you can't quantum mechanically in the vacuum. This is a reasonable description of the quantum fluctuations that exist in the vacuum because of quantum chromodynamics at the length scale of the proton. So this is the size of the proton in this simulation, which comes from calculations in lattice QCD. Now we have to rethink the interaction between these quarks, because these charged particles are now in a medium, a complicated medium with its own properties. And asymptotic freedom essentially was the discovery that in this kind of theory of the strong force, which says it's exactly the same kind of theory that you use for electromagnetism, except with 3 charges instead of 1, is that this medium squeezes these flux lines as much as possible and squeezes them, so they don't spread out like this, to a tube, which as much as it possibly can. That essentially is the essence of asymptotic freedom. And we can, on the basis of that, explain why you've never seen a quark. You actually probably haven't seen an electron either, but you felt it sometimes when you know, maybe not in Seattle because it's too humid, but in deserts like Santa Barbara, you walk and you feel electrons. But you never felt quarks, and that's because these flux tubes, you see, now are, these lines of force are squeezed into a tube with a fixed area, no matter how far apart you pull the quarks. And if you apply Gauss's law again, now the area is fixed, independent of the distance between the quarks. So the electric field here must be the same, because you have a source. Gauss's law says the source times the area which these flux lines pass is the charge. So the electric field, which is proportional to the force the quarks feel, is constant at any distance. And if you have to overcome a constant force, then the energy it takes increases linearly with separation. And instead of getting an ionization curve, you get the energy goes up forever. It would take an infinite amount of energy to truly separate the quarks. That's why you've never seen a quark. The quarks are so strongly bound that they come together to form neutral objects. And the only way you can see a quark is if you can get inside those neutral objects. What are the neutral objects? Well, the proton is a neutral combination of these 3 colors. You put together 3 primary colors, red, white, and blue, you get white. So that's asymptotic freedom, and it led to our understanding of quantum chromodynamics, QCD. This is actually what it looks like in the theory when you try to pull a quark together. You see these flux lines creating a flux tube. Flux tube looks like a fat string. This is where string theory actually came from. So that explains why you've never seen a quark. But conversely, when the quarks get closer and closer together, the force gets weaker. So it's exactly the opposite of what intuitively you might think. And that means you can see quarks all right, but only if you have a microscope that's good enough to see inside this fat flux tube. That can be done. That's what we do at these high-energy accelerators. We scatter protons, which are made out of quarks. What we are really scattering are bags of quarks, and we can, if we're clever, see the quarks scattering inside the proton. And the decrease of the force law, this is the strength of the force between the quarks, gets weaker and weaker as you go to higher energy, probing shorter distances. Conversely, stronger and stronger when you go to larger distances. Now this, like the rest of the Standard Model, as I've said, is impressively successful. Every new accelerator for the last 30 years, especially now the LHC, has confirmed the predictions of all of the standard theory, including QCD. These are fits that explain a good portion of those pictures of the complicated events you see in those collisions over something like a factor of 10 to the 11 to 10 to the minus 1 of a billion times a billion accuracy with incredible precision. For a theorist like me, the most satisfying success of this theory is the ability to calculate our mass, the mass of the particles the quarks are made out of. I often ask audiences, what do you think is the origin of your mass? And they say, well, it's a physicist. Not the meal I had yesterday, but rather the atoms I made of. Every atom weighs something. Well, what is the origin of the mass of the atom? Well, the mass of the nucleus. That's where most of the mass is. And what's the mass of the nucleus come from? Well, they know the nucleus is made of quarks, so it comes from the mass of the quarks, which is totally wrong. Quarks are almost massless. They're like particles of light. The only reason they're traveling very fast within the proton, they don't get out because this force gets stronger when they try to get apart. So they go like this, very fast. They don't have any rest mass to speak of. You could neglect that. You wouldn't be too far off. Your mass is simply confined energy. Some people really like that when they've gained a pound. It's all confined energy. But that also means we can really calculate the mass of the proton and the neutron and all the particles that quarks can make up. And this is a great triumph of lattice numerical approaches to the solution to quantum chromodynamics. And this is a beautiful comparison of these measured values of all of these particles, which when I was a graduate student were being discovered all the time and nobody had any idea what they were. We can now calculate sometimes with accuracy of 1%. Well, so standard model is great, but theory, experiment, science thrives on not on success, but on failure. Not on knowledge, but on ignorance. Not on what we've already understood, but the open questions. And there are many reasons why their standard model, as successful as it is only part of the story. There are experiments. I said standard theory works, explains just about everything, but this is the just about part. Astronomers have discovered that most of the matter in the universe is not made out of quarks and leptons. Some other kind of matter. Neutrinos have a mass. You can easily tweak the standard theory to account for that. No big deal, but we don't know exactly how to tweak it yet. There's a lot of matter in the universe. I mean, we're made out of matter. And you'd think there should be an equal amount of antimatter, but there doesn't seem to be. Why the difference? There's no principle in physics. This we should be able to understand, but we don't yet. There's the dark energy, cosmic acceleration. These are clear experimental aspects of the universe and of particle physics that are not addressed yet by the standard model. These are just direct experimental clues. But there are also theoretical clues. unification of all the forces, which I'll speak about. There are some weird things about the numbers, the parameters that we can't calculate, must take as input. For example, the masses of the quarks. We don't know how to calculate them, and the pattern of masses of the quarks as measured is quite bizarre. And then there are issues having to do with the structure of the universe, inflation, and the vacuum energy. We're now doing experiments in a new domain, that of a TV. And some of these questions, we believe, for good reasons, we hope, can be addressed for sure experimentally in this regime, especially an idea that has motivated much of theoretical research in the last 30 years, which is a new symmetry called supersymmetry. I'll say a word about. But let me first talk about unification, the search for unification. It's nice to unify things. But it's also been a very successful strategy in physics. Maxwell unified electricity and magnetism. Even before Newton, in his theory of universal gravitation, unified apples and planets. You know, before Newton, nobody would think of that the motion of apples and planets had the same source. The Standard Model doesn't really unify all the forces. We still have three separate forces: the electromagnetic force and the weak and strong nuclear force. And it doesn't really unify all the matter. We have quarks, and we have leptons, and then we have the Higgs. Now, when you're faced with a situation like this, you ask yourself, could this really be simplified, be all part of some bigger unified scheme? Doesn't have to be. It's like somebody gives you pieces of a jigsaw puzzle, and you're supposed to put them together to make a picture. And you work hard, and you can't succeed because you lost a few of the pieces. They fell on the floor. Could have been the case here. Anyway, you should obviously try. If they don't fit together, that suggests where to look for the missing piece. And if they do, it might tell you something about unification. So this happened very shortly after the Standard Model was completed in the middle 70s. Remarkably, these three forces and these two kinds of matter actually, with what was already known and partially confirmed experimentally in the 70s, fit together beautifully. And the following 40 years, nothing really has been, except for that dark matter stuff, has been discovered that threatens this incredibly simple picture of a unified theory in which all of those forces somehow were unified into one force, and all of the matter somehow unified into one form of matter. That, of course, begs the question, why do they look like three forces when we do experiments in the real world, with the LHC? Wherever we've been able to do them, we see three very separate forces. That we can explain. The underlying reason for all the forces in the Standard Model are symmetries. And unifying those forces is imagining an even bigger symmetry. And we have learned how to imagine, sometimes prove, certainly observe the consequences of those symmetries being broken, not manifest. And that can happen as a function of scale. Much as, the physics in this room, if I look at very short scales, has very little structure. But at large scales, it looks very different. Basic laws of physics are rotationally invariant. They don't change if I turn my laboratory. That's true of physics at very small scales in this room. If I do an experiment in this room, it won't matter which direction my instruments are pointing. But at large scales, well, you guys are there, but not there. That rotational symmetry is broken. The same can happen here. It could be that at very short distances, we see one force and one form of matter. But at larger distances, symmetry breaks and the forces seem different. Not only that, the forces can have different strengths as a function of scale. And they could very well be the same at very short distances or high energies. That's already the case of, that's what asymptotic freedom is. It says the strong force gets weaker when you bring the quarks together. That's also true of the weak force. The electromagnetic force works in the other direction. It gets stronger when you bring the charges together. So extrapolating these forces, it could be, and it turned out to be the case, already in the early history of the Standard Model, the forces seem to unify. And they unify at an extraordinarily high energy. Of course, they change very slowly as you go to higher energy or shorter distances. This picture is extraordinarily important for our field. It's a wonderful clue, perhaps, to many things: unification, the incorporation of gravity. It happens to be that this is the scale where gravity becomes a strong force. Now, some audiences are surprised when I say, when gravity becomes a strong force. Gravity is a strong force. I mean, for most of us, that's the only force we ever feel. Get up in the morning, you feel gravity, right? And you don't feel the other forces. The reason you don't feel the other forces is that they're all these forces like electricity and magnetism, or QCD. They have one kind of charge that attracts another kind of charge, and you bring them together, and they cancel and give you a neutral object, which has very little residual force. Molecular forces. Gravity acts on everybody. It's universal. So the only reason you feel gravity is that the whole Earth is pulling on you. You don't feel a gravitational attraction to your neighbor, but you do to the whole Earth. That requires 10 to the 57 atoms pulling on you before you feel that force. Gravity is 10 to the 40 times weaker than electricity inside the atom. But at this energy, gravity becomes strong. So you can take this picture and say that's a very important clue, which I believe, for the unification of all the forces, perhaps with gravity at an extremely short distance or high energy. But the trouble with this kind of physics, and the trouble with being a theoretical physicist exploring this kind of physics, is that for all we know, that could be a coincidence. And we don't have many such clues, 3 or 4 or 5. And now this unification, if it's true, would mean that if you could do physics and observe these energies, or look at these very short distances, you would see totally different kinds of physics. All the forces would behave similarly, including gravity, perhaps. But it also tells you what the scale is. This is, see, 15 orders of magnitude. You need a particle accelerator that is 1,000 million times bigger, more energetic than the LHC. And that means probably 10 to the 30 times more expensive. In fact, it would have to be of size of the galaxy, perhaps, with existing technology. So we can't directly probe this scale, which is picked out by this important clue. But we have been led to other ideas. And I mentioned supersymmetry before, and I'd like to say a word about that. So symmetry, not of objects, but of the laws of physics, has been a dominant theme in understanding fundamental physics since the turn of the last century, starting really with Einstein. And Einstein built his understanding of relativity and then general relativity on the symmetries of the laws of physics in space-time. So objects live, events take place in space-time, and there's symmetries of the laws of physics under transformations of space-time. For example, the simplest one I already mentioned, rotational invariance, right? If I do an experiment, here's an experiment. I drop it, measure how long it took to drop. Now I rotate my laboratory and do the experiment, I get the same result. The laws of physics don't change when I rotate in space. That's very useful. It means when I do an experiment and publish a paper reporting my results, I don't have to say in which direction my laboratory was pointing. I don't even have to say where it was, Seattle or New York. That's translational invariance. The laws of physics are invariant under translations in space. I don't have to say exactly what time I did the experiment. So the laws of physics are invariant under translations in time. Well, supersymmetry is simply rotations in superspace. But I have to tell you what superspace is. So superspace is a bigger space with more dimensions, you know. In addition to x, y, z, and of course time, I have theta. And the reason it's called superspace is that these extra dimensions are super. They're measured not with ordinary numbers, but with super numbers or Grassmannian numbers whose multiplication law depends on the order. So, you know, theta 1 times theta 2, two of these numbers multiplied in this order or in this order give opposite results. Mathematicians can invent all sorts of crazy numbers, and they're perfectly sensible. Square root of -1. So these are Grassmannian numbers. There's a nice mathematical framework. You construct a model of space-time in a space with extra these anti-commuting theta-like coordinates. Remember, space-time is not real. Have you ever seen space or time? Space-time is a mental construct, a model of reality that in our greatest intellectual achievement, every single one of us has constructed as our brains were developing as infants in order to crawl across the room and get the toy. We construct a model. Well, infants do it. How they do it, who knows? We all did it. This model, you know, is simple to describe. We've had to revise it over and over again in the 20th century due to special and general relativity. It's now being threatened as well in ways I'll describe in a moment. But it's perfectly possible that it's inadequate, and we actually live in a space with these anti-commuting coordinates. And it was discovered that there's a fantastic generalization of ordinary physics to physics living in superspace, and all the theories we've ever had can be generalized to superspace. And it has a lot of advantages. That unification of the forces doesn't really work in the standard theory. This is a better, more modern extrapolation. And these are the three forces, or the inverse forces, which are as a function of energy on this logarithmic plot are straight lines, and they don't meet. If you had supersymmetry, they do, with the additional hint that that supersymmetry breaking, you should start seeing the supersymmetry when you get down to distances or get up to energies that are now being explored at the LHC. So this is great. This is a very important clue for supersymmetry, a clue as to where you might see it, and unification, or a coincidence. But there's another clue. There are very few clues, so each one is important to discuss. This is a big one. This is dark matter. Astronomers discovered that stars and elliptic galaxies like ours, are moving too fast to be accounted for just by the matter that you can see. So there must be extra matter, which is you can now see by other means, gravitational lensing. And they have convinced themselves and us that most of the matter in the universe is dark. By dark, it means probably something like a very heavy particle, just like a proton or uranium nucleus or something of that order of magnitude and size, but one that doesn't couple to the particles we're made out of, and in particular to light. So we can't see it directly. But of course, like everything, it exerts a gravitational pull and makes the stars and the galaxies go around, and explains in the standard cosmological model pretty successfully how galaxies emerge. But we don't know what these particles are. And again, supersymmetry predicts a candidate for dark matter. Not that there aren't other candidates. Axions are being searched for here, and that's another possibility. But supersymmetry does predict a candidate naturally, and again, picks out a TV scale. So you can take that as an important clue for supersymmetry at a TV, or a coincidence. Oops. So at the LHC, they're looking for something like this. This would be a picture of an event where the protons come together, lots of stuff, comes out in these jets. You can just see by eye that it's somewhat unbalanced. If all this stuff is going this way, something must be going this way. You can indeed measure the missing momentum and energy that in perhaps a heavy particle that just doesn't interact with the detector. Neutrinos are seen this way. And that could be a sign for dark matter. And many of us are waiting for the LHC to announce that they've discovered something like supersymmetry. Perhaps they will, perhaps they won't. But I do want you to remember that if they do discover supersymmetry, what they're really discovering are quantum dimensions of space-time. We, again, will have to revise our notion of what space and time are. And even though that symmetry is not manifest unless you look at very microscopic phenomena. The laws of physics would be describing events or fields in this extended superspace and would be invariant under rotations in that superspace. So this would be the correct, as we will have learned if it happens, description of the arena in which we describe physical reality. Well, I'm running out of time. So I want to describe very briefly where particle physics is, which is really uncertain. It's always uncertain. But it's a bit, particle physicists, as all scientists I've noticed, tend to oscillate rapidly often between optimism and pessimism. You see a bump, it goes away. You have an idea, you made a mistake. Most active scientists, certainly in this field, I think, are optimists. It's very simple. The pessimists simply quit. So, but you could be pessimistic about high-energy physics. After all, we discovered this new Higgs particle, as predicted, sort of, but it could have been different. It seems to fit. And in the pessimistic scenario, even that new discovery, a new portal, perhaps onto new physics, which many were hoping for, doesn't materialize. Supersymmetry, this beautiful idea, solves many problems. Could be wrong, not detected. Dark matter, which is being searched for to understand its properties, in the sky by seeing annihilation of dark matter, underground by seeing the dark matter wind, detecting it, or producing it at the LHC. Well, so far all of these have failed. They might continue to. And the worst thing about this field is that the only obvious places where everyone would bet that there has to be something new and fundamental is way up there at the unification or the Planck scale, or maybe smaller scales, but only by a factor of 1,000,000 or so, not enough to observe directly. That's the pessimistic scenario. What should the field do if that turns out to be the case in, say, 5 years or a few years from now when the LHC is measured up? Well, in my opinion, the obvious thing to do is to fully explore the next scale of energies that we can explore. In fact, we already built the next generation accelerator. It's called the SSC. It was unfortunately canceled just as it was underway by the precursors to the Trump phenomena. But it's quite achievable. And if we arrive at this pessimistic place, we must do what we already almost did to exclude the obvious possibilities. In the extremely optimistic scenario, we will see new physics even in the Higgs sector. There might be some evidence of something like a heavier object that there's some indications they've seen already. We might produce supersymmetric particles, detect dark matter, and have strong guidance for the next steps, in which case the obvious thing to do would be to explore the new world that's being revealed by all of these new elements of physics. So in both cases, the future is clearly to explore the next order of magnitude in energies and distance scales. And there are many plans underway to do so. The one I think perhaps is most exciting is the last, because it involves a new major economic player which has the ability and perhaps the will to contribute to basic physics. And there is a strong proposal coming from China to build a large collider, which I've called the Great Collider. And it would be located around here, the very town on the coast of northeastern China, where the Great Wall was started. If we come back to this picture of unification and notice that gravity becomes strong, that leads and has led many of us in a totally different direction. How does one incorporate gravity together with these other forces? String theory does that. And it has sort of dominated the research into a potential unified theory now for many decades. So, as I said, string theory originally emerged from people trying to understand the strong nuclear force, which we can understand now as the fact that these tubes, flux tubes, quark, antiquark, look like fat strings. So many of the properties of QCD objects are sort of like string properties of fat strings. And that correspondence between gauge theories, these theories like electromagnetism or QCD, quantum chromodynamics, and string theory, has only gotten stronger over the years and has now developed to a correspondence between the quantum field theories we use to describe the standard model and this new objects string theory, in which the basic objects are not point-like particles, but extended strings. The other thing that string theory has taught us is the relation with gravity. String theory, these open strings, these flux tubes, can be closed, and when they're closed, they describe gravity. We had much hopes at the beginning of string theory that simple exploration of this idea, one could describe all of those elementary particles and all of those forces as different vibrations of a single superstring. That was premature optimism. But it's raised a whole host of credible new ideas, new possibilities, and new understanding. For example, and most importantly, I believe, it threatens many of the other aspects of our naive picture of space-time, our most fundamental concept that we all developed when we were infants. For example, why are there only 3 dimensions? This way, that way, and that way. And this question that was forced on you in string theory, where it actually, in the simplest way of looking at things, there have to be more dimensions. In fact, 6 extra dimensions. Since they're not seen, they better be curled up so you can't see them. And that's a possibility. String theory suggests that, indeed, one way of looking at it, that at every point, everything we think is a point, if we could look with a microscope, we'd see an internal space, other directions, 6 other directions, all curled up in a beautiful structure. Could be the case. Hard to know, since, again, the size of these extra dimensions would be of the order of maybe a bit larger maybe 1,000,000 times larger, but we only see distances which are 1,000,000 times 1,000,000 times 1,000 smaller, so we can't tell. But in this approach, what is so beautiful is that many of the features of the standard theory that we have no way of understanding within the standard theory, questions like, or numbers like the values of the quark masses, or questions like, why are the forces what they are, these electricity, magnetism, strong nuclear force? Why is there matter at all? Where does it come from? All of that is determined in this kind of string model by geometry, by the shape of the internal dimensions. The Greeks would have loved this. You answer all of these complicated questions, these funny numbers, in terms of geometry. Well, you can write down such models, do such calculations. They're very hard. And there are people trying to match explanations like this that follow from string theory with what we measure and make predictions about what would be measured. But we have a bit of a problem. And the problem really is if I try to now ask, what is physics? What are the basic principles of physics, what I call the framework of theoretical physics? The standard theory is a so-called quantum field theory. It's built on these electromagnetic fields, these chromodynamic fields, and then it's a quantum mechanical theory. It's what we call quantum field theory. That's a very bad name because it's not a theory. You can't calculate anything. You could test some of the basic principles, but it's a framework, like quantum mechanics. Then we have something called string theory. If you ask a string theorist, what is string theory, you'll cause much problems. Because they'll say, well, it's a theory of string. You keep pushing, what is it? They won't be able to tell you. It's not a theory either. It's a framework. The remarkable thing in the last decade or more, we've discovered that these two frameworks are actually identical. They're the same framework. Fascinating phenomena, and we have some very precise examples, can be described either by the standard model-like theories in this framework, or in terms of strings in this framework. This is very useful. People trying to understand high-temperature superconductivity are now trying to construct models of quantum critical behavior using solutions to Einstein's equations coming in string theory in higher dimensions. You can use one description to learn about the other description and vice versa. None of these are theories. These are all frameworks. The standard theory that I wrote on the T-shirt is a theory. You can calculate, compare with experiment. What we have instead at this point is an incredible framework that includes descriptions of often the same physical phenomena in terms of field theory, strings, higher dimensional extended objects, and that gives us a way of understanding quantum gravity. But at the same time, it raises really serious problems now, both with space-time and with cosmology. So I'm going to end now at the true frontiers where we know very little. With respect to space-time, this, in the string theory part of the framework, we've learned that many of the properties that we ascribe to space aren't so solid. For example, that it's smooth, or that it has a fixed topology, or that it even has a fixed number of dimensions. we suspect more and more that this crude picture of space-time we've constructed as infants and changed over the centuries is fundamentally approximate. Space-time is an emergent concept, good for describing much of physics, but not at these very short distances or other extreme conditions, and really should be thought of as emergent. This new understanding of the enlarged framework allows us to explore this possibility and see what underlies space-time, what is space-time made out of, but it's not easy. And in particular, we really do away with space-time, replacing it by an emergent concept, especially time. It's hard to formulate what the rules of physics are. But the other problem is, if you ask yourself, what picks out a theory? What fixes the dynamics? That's not something you know also what the rules are. The standard theory is so successful because we're unable, or we can't, answer the question, what picks out this particular theory? But in this enlarged framework, including strings and quantum gravity, we have to face up to that question. Sometimes it's framed in terms of a landscape, anthropic arguments. And another way of stating it, which we have to face, is what fixes not just the dynamics, but the initial state. And that's because if we unify gravity into the game, we're discussing dynamical space-time. That's what gravity is, the dynamics of space-time itself. The dynamics of space-time is the universe. You can't avoid, if you have a theory of the universe, to have a theory of the Big Bang, the beginning. So a question like how the universe began is not one that you can avoid. What the initial condition is no longer a question that you can avoid if you're actually trying to understand what picks out the particular theory in the framework that you would compare with experiment. Another way of saying this is that Einstein taught us that the universe is the history of space-time, which has a beginning and maybe a boundary at the end, and the answer to a unified theory of gravity and the other forces is a consistent space-time history, including the beginning, maybe the end. And here we're faced with a problem that physics has always been able to avoid, but perhaps not now. And we don't know what the rules are. So this really defines what the farthest element of the frontiers are, when not only are you clearly ignorant of what the answer will be, but you're also ignorant of the rules that you should be employing. So we have a wonderful theory, but the most exciting questions, the beginning of the universe, the nature of space-time, the values of the quark masses, why are the forces with it, et cetera, remain to be answered. We have a lot of handles, experiment, instruments. We can build and will, I hope, fantastic speculations. But the best is yet to come. So can we go on forever? Another way of putting it is you have this series here, the frontiers of fundamental of physics. Can it go on forever? Well, let's say, at least in this reductionist portion of physics, we succeed. We construct the theory of everything, the final theory. So we're finished. The other issue is that we simply might be too dumb to succeed. And finally, we might lose the will to proceed. So, is there a final theory? Is there a theory of everything? Is there an end point to this kind of search for fundamental laws and fundamental constituents of matter? So, in my opinion, this is an issue of geometry again, the geometry of knowledge. So, there is a model of knowledge in scientific exploration, which I don't particularly like, but it's called the onion model. And nature is like an onion. You peel away, you find the truth in the center, and this model brings tears to my eyes. It explains nothing new, and it's exactly the opposite. We're in a bubble of knowledge pushing outward into a sea of ignorance. So, onion inverted, turned inside out. And this model explains something that we all learn at an early age about knowledge, ignorance, and wisdom. So this is the sphere of knowledge expanding throughout the sea of ignorance. But the ignorance we're aware of, right, is only on the border of the sphere of knowledge. So ignorance out here is, as Rumsfeld said, the unknowable unknowns. But right on the border, that's what you're aware that you don't know. So in this model, knowledge increases like the volume of the sphere, and ignorance like the surface only. And that's, somewhat depressing when you're a young student. You realize the more you learn, the more you realize you don't know. On the other hand, the ratio of knowledge to ignorance increases because the volume increases faster than the surface. So this model explains why as knowledge increases, so does ignorance, but so does wisdom. So now that we've tested the model explaining something we all know, let's use it to ask whether we can construct a final theory. So that, turning it around, this is the question, is there a finite amount of ignorance? I mean, if you have a final theory, you've eliminated all the ignorance. Now, this has happened before, the exploration of the Earth. This is a medieval Eurocentric picture of the world, the known world, and the borders of the known world, which is where the ignorance is. And there were explorer societies exploring the Earth. And they ran out of ignorance. I mean, the Earth is round. Sooner or later, they, at least at the scale of a kilometer or so, they had final map of the world. Right? Don't need to do any better. That's it. Explorer society shut down, by and large. So the question is the sea of ignorance compact? In other words, this is a topological question. Is it like a flat Earth, unbounded and infinite? Could be. In which case, knowledge will increase forever, ignorance will increase forever, wisdom will increase forever, and jobs in science will go on forever. And this lecture series can go on forever. But it could be like the Earth, compact and finite. And eventually, ignorance starts decreasing, and you run out of it after a while. Now, of course, that wouldn't be the end of physics, because most of physics and most of the marvelous features of physics are not in this reductionist fundamental direction, but rather in the infinite structures and phenomena that could, in principle, be all derived from here. But on the other hand, I don't know, actually. I'm totally agnostic. There's no sign of curvature. I don't see any horizon. Could be flat. Who knows? But the other problem is, of course, even if the sea of knowledge is flat, or even if it's compact, we simply might be too dumb to figure it out. Why should we, Homo sapiens, who've only been here for, a few million years, why should we imagine that we're so smart, so clever that we could figure out what are the principles that determine the initial condition of the universe or the nature of space-time? We certainly, you would think, didn't evolve to do that. And we know that our fellow species can't, right? You know, I cannot teach my dog quantum mechanics. You laugh because you know that's true, right? You know your dog can't comprehend quantum mechanics. Now try to think of something you can't comprehend. It's hard, but why do we have the arrogance to believe that that's not the case with us as well? Well, I told you I'm an optimist. I don't think that's a problem either. And it's partly because the one thing we possess as a species that makes us different and has been responsible for our success, at least in science, is language. Mathematics is the most evolved form of language, and it has infinite capacity, even ordinary language. Chomsky pointed out that an infant picks up language without any real instruction, just by listening, and is able, having picked up English or Chinese, to utter sentences that have never been uttered before. So language has this infinite capacity, as does mathematics. Maybe it's not a big enough infinity, but at least it's infinite. The other thing is that if we were getting close to such a point in history, in our evolution, that we were faced with conceptual problems that are like quantum mechanics for the dog, simply beyond our ability, I think we would begin to notice it. And one experimental test would be how long it takes a graduate student to get a PhD in physics. Now, it's true that that has gotten a little bit longer, but it's still the case nowadays that students, go through all of this incredible development of the last few hundred years, and at the age of 25 start doing work at the frontiers of knowledge. That hasn't changed. So that's a sign that we're not yet approaching the same obstacle that the dog has when the dog tries to go from classical physics to quantum mechanics. There's no sign that we're faced with questions that can't be answered. But if the PhDs start getting delayed till the age of 70, might be a sign that... I think the real danger of going on forever in this, or for a long time even, is that we'll lose the will and the means, and society at large will lose the interest in to support this goal. And here, again, I don't know. I simply hope not. And I love this quote on David Hilbert, the great German mathematician, mathematical physicist. On his grave, you can see it says in German, "We must know, we will know." Thank you.